Welcome to Electrical Science Part 2, where we'll explore the fascinating world of AC circuits. AC, or alternating current, is different from DC because the current and voltage in AC circuits periodically reverse direction. This happens in a sinusoidal pattern, meaning it alternates smoothly, like a wave. AC operates at specific frequencies, such as 50 Hz in India and 60 Hz in the USA. These alternating characteristics make AC ideal for efficient power transmission over long distances, which is why it's widely used in both households and industries. A sinusoidal waveform forms the basis of AC circuits. This wave smoothly oscillates between positive and negative values, representing the alternating nature of current. The equation for a sinusoidal waveform is Vt equals V peak times sine omega t plus phi, where V peak is the maximum voltage. Omega, angular frequency, is calculated as 2 pi f, with f being the frequency. Phi is the phase angle, showing where the wave starts on the time axis. For example, in household power with a 50 Hz frequency, the current direction changes 50 times per second. These waveforms make AC systems efficient for generation and distribution. Peak and RMS values help us measure AC waveforms. Peak value is the maximum amplitude of the waveform. For instance, if the RMS value of household voltage is 240 volts, the peak value can be calculated using the formula. V peak equals square root 2 times V RMS is almost equal to 339 volts. RMS, root mean square, value is the equivalent DC value that delivers the same heating effect. For a peak voltage of 339 volts, the RMS value is approximately 240 volts. RMS values are crucial for specifying electrical systems because they give a practical measure of the energy delivered. Phasors simplify the analysis of AC circuits by representing sinusoidal waveforms as rotating vectors on a complex plane. A phasor captures both the amplitude and phase angle of a waveform. For example, the sinusoidal function Vt equals 100 sine omega t plus 30 degrees can be represented as a phasor, V equals 70.7 angle 30 degree. This means the RMS value is 70.7 V and the phase angle is 30 degrees. Engineers use phasors extensively in power systems to calculate voltages and currents efficiently. Power in AC circuits is categorized into 3 types. Real power, the actual power consumed, measured in watts. It's given by the formula P equals V RMS times I RMS times cos theta, where theta is the phase angle. Reactive power, power stored and released by inductors and capacitors, measured in VAR, volt-ampere reactive. Formula Q equals V RMS times I RMS times sine theta. Apparent power, the total power in the circuit, calculated as S equals V RMS times I RMS, measured in VA. Understanding these components helps us analyze energy usage and efficiency in electrical systems. This diagram represents the power triangle, a visual representation of the 3 types of powers. Power factor measures the efficiency of power usage in a circuit, defined as the ratio of real power to apparent power. Power factor equals cos theta. For example, if voltage is 120 volts, current is 10 ampere, and the phase angle is 30 degrees, the power values are real power, P, is equal to 120 times 10 times cos 30 degrees, is almost equal to 1039 watt. Reactive power, Q, is equal to 120 times 10 times sine 30 degrees, is almost equal to 600 VAR. Apparent power, S, is equal to 120 times 10 equals 1,200 VA. A high power factor reduces energy loss and improves efficiency, which is why industries prioritize power factor correction. When we combine basic components, resistors, inductors, and capacitors, each affects the circuit differently. Their unique properties create distinct relationships between voltage and current, which we'll explore in detail through each combination. In a purely resistive circuit, the voltage and current are in phase, meaning they reach their peaks simultaneously. The impedance is simply the resistance, Z equals R. Power is entirely real, calculated as P equals V times I. For example, with a voltage of 120 volts and resistance of 10 ohms. Current, I equals V/R equals 120 divided by 10 is equal to 12 ampere. Real power P is equal to 120 times 12 equals 1,440 watt. Applications include heating devices like electric stoves, where all energy converts into heat. In inductive circuits, current lags behind voltage by 90 degrees due to the inductor's opposition to changes in current. The impedance is purely reactive, Z equals JXL, where XL equals 2 pi FL. Reactive power is significant, while average power over a full cycle is 0. Applications include transformers and motors, which rely on magnetic fields. In capacitive circuits, current leads voltage by 90 degrees because capacitors resist voltage changes. The impedance is reactive, Z equals minus JXC, where XC equals 1 by 2 pi FC. Reactive power dominates, and average power over a cycle is 0. Capacitors are used for power factor correction and in tuning circuits. In an RL circuit, the inductor introduces a lagging phase angle between voltage and current. The impedance, Z, is a combination of resistance and inductive reactance, Z equals square root R square plus XL square. Current is determined by Ohm's law, I equals V divided by Z. RL circuits are commonly used in filters and transformers. In RC circuits, the capacitor causes current to lead voltage. The impedance is a combination of resistance and capacitive reactance, Z equals square root R square plus XC square. Current is found using Ohm's law, I equals V divided by Z. RC circuits are widely used in timing applications and filters. RLC circuits combine resistors, inductors, and capacitors. The total impedance includes resistance, inductive reactance, and capacitive reactance, Z equals square root R square plus XL minus XC square. The phase angle determines whether the circuit behaves inductively or capacitively. At resonance, XL equals XC, and the circuit acts purely resistive, minimizing impedance. RLC circuits are key in applications requiring resonance, such as radio tuners. Resonance occurs in an RLC circuit when the inductive and capacitive reactance cancel each other out, making the impedance purely resistive. At resonance, the circuit's energy oscillates between the inductor and capacitor, enabling frequency-selective behavior in communication systems. Let's look at how these circuits are used in real life. Resistive circuits, found in heating devices where electrical energy is fully converted into heat. Inductive circuits, used in motors, transformers, and devices relying on magnetic fields. Capacitive circuits, applied in power factor correction and frequency tuning. RLC circuits, essential for creating resonance in radios, TVs, and communication systems. Three-phase circuits are a cornerstone of industrial power systems. A three-phase system has three AC voltages of equal frequency and amplitude, but their phases differ by 120 degrees. These systems offer advantages like efficient power transfer, reduced conductor material, and the ability to carry more power than single-phase systems. Three-phase circuits are used extensively in heavy machinery, HVAC systems, and industrial equipment. In a star connection, three components are connected to a common neutral point. The line voltage, VL, is square root 3 times the phase voltage, VPH. The line current, IL, equals the phase current, IPH. In a delta connection, three components are connected in a closed loop. The line voltage, VL, equals the phase voltage, VPH. The line current, IL, is square root 3 times the phase current, IPH. Delta connections are widely used in industrial applications for high-power loads and balance systems. Star and delta connections serve different purposes in three-phase systems. Star provides higher voltage at lower current, suitable for distribution networks. Delta provides higher current at lower voltage, ideal for high-power industrial equipment. Understanding their differences helps optimize systems for efficiency and cost-effectiveness. We've reached the end of this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.